and welcome back to another lecture of Statistics 479 Time Series Analysis. Today, what we'll be doing is continuing our discussion of estimation of the spectral density, because we're not done with it yet. So when estimating the spectral density, we already figured out it's the periodogram, and it works pretty well, but we can do better. We can consider other methods of estimation, like do we really need all of those frequencies? We could actually reduce the number of frequencies where we estimate the spectral density, and instead get better estimates for the frequencies that remain. We can also consider the idea of banding. That is, we could average local frequencies together to get a better estimate. And beyond that, we also have the idea of tapering, smoothing, and lots of other cool techniques that we'll be talking about in today's lecture. So, let's go check out the notes. And welcome back to another lecture of Statistics 479 Time Series Analysis. Today we're going to continue our discussion of estimation of the spectral density. It's really an important part, because we ultimately want to know what the spectral density is, well, what it looks like, because it's going to tell us a lot about our time series data. The problem is that estimating it is not straightforward. In the last lecture, we talked about the periodogram and how the periodogram is a good estimator, but there's a lot of issues that we could consider with respect to the periodogram. Do we want to just take it as it is? Do we want to, say, remove some of the frequencies and estimate other ones? There's lots of different ways we can approach estimation of the spectral density depending upon what we're interested in. And we're going to talk about a bunch of those methods today, including banding, tapering, and other smoothing methods. Now, at the end, there's no right answer, right? We're going to talk about a bunch of methods today. None of them are like the right choice. They're all just different ways of looking at the spectral density, and we can try, in some sense, many of them when looking at some time series. Remember, time series is really an exploratory type of subject. We're just going to have to try different methods and see what we get. And this section is very much like the smoothing methods that we talked about at the beginning of the course. There's no like right or wrong smoothing method. You just have to choose one or try more than one and play with the parameter until you get something that tells you what you want to know. And similarly, today we'll be looking at a variety of methods for estimating and smoothing out the estimating the spectral density via the periodogram. And similarly, we'll have to try a bunch to see how they work out. And we'll do that, but we'll do that probably in the next lecture in R. For now, we have to talk about what this stuff is all about. So, let's get into the notes. All right, so this section is estimation, not S. Estimation of the spectral density, Part 2. All right, so what are we going to talk about first? Well, the first thing I want to talk about is, Bartlett's method. So Bartlett is a name you might have heard before. We know about Bartlett's test for homogeneity of variance. It's a standard one that you would use, say, if you're doing, ANOVA, and you want to know if your categories have the same variances. Well, Bartlett was a smart guy, and he also came up with a way to estimate a periodogram, or estimate the spectral density from the periodogram. So the first thing we'll talk about is Bartlett's method. And the idea behind this is simply that for a time series, x1 through xt, we get, or we got, I guess last time, we get a periodogram that we can evaluate at omega j for omega j equal to j over t. So that's a lot of different frequencies if t is big, right? If t is 2000, you're going to have a lot of different Sorry. It's been a long term. We're almost there. Let's keep doing time series. All right, so what I was saying is that if t is large, we have a very fine granularity. We can estimate a lot of different frequencies, or we can evaluate the periodogram at a lot of different frequencies. But we may not need all of those omega j. Instead, we might want to have fewer frequencies, but do a better job at estimating them. So how do we do that? So what we can do is instead split the time series into, what was my notation? I think K. Yeah, K separate, equally sized, this is kind of important, pieces. So what I mean by that is you start with your x1 through xt. And then what we're going to do is we're going to break this thing up. And we're going to create some pieces. We're going to have, say, x1 through x. What was the notation I was using? Oh, k. K separate disjoint series of length m. Okay, so that notation is wrong. What I wanted to say was x through m. I need another variable in here. We're going to define m to be the length, which is going to be t divided by k. So what I'm doing is I'm taking my big T data points and I'm splitting them into k chunks, and each of those chunks is going to have m observations in it. So we'll start here from m plus 1, go all the way up to 2m, and this will continue until we have our final piece, which would be what? I guess it's going to end at, well, I guess k, well, it's t minus m plus 1 all the way to the final point. So now what we can do is we can take each of these sub time series pieces and we can compute a periodogram via the DFT. So we get a periodogram number 1, we can get a periodogram number 2, and we can get a periodogram number, I guess, k. Right, so in this case, what we will do then is we will aggregate all of these periodograms to get our new estimator. So in this case, we take these all and we determine that the new periodogram, I omega j, is going to be the average. Here, 1 over, I guess there's k of these guys. So we're going to average over all k of them and take I from 1 to k of I to the I. Not the greatest notation, but, you know, it works. Omega j. All right, so what is the effect of using this new estimator via the Bartlett method? Well, the idea is that now we have omega j is going to be j divided by not capital T, but lowercase m. So fewer omega j's to consider. But, and this is the sort of the big but, the point is that we get a smaller variance. And that's the nice thing here, right? We have this smaller variance because what we're ultimately doing is we're estimating the periodogram at a given frequency, k independently k times, and then averaging over all of those observations. So this will, as often happens in statistics, reduce the variance. It just means that we don't get as many frequencies as we would have before, but that's okay because typically we don't need such fine granularity. If we have, I don't know, 496 data points, we probably don't need all of those frequencies. We could cut it in half a couple times, and maybe just have frequencies from, 1 to 128, say, but have a better estimate by reducing the variance. So that was Bartlett's method. And, oh, there's one other thing to note. Also, note that k DFTs of size m are faster to run than 1 DFT of size t. Remember that the discrete Fourier transform is, if I recall, it was quadratic complexity. To double check my notes earlier up, but regardless, it's beyond linear, which means that if I break this up linearly into a bunch of chunks, it's faster to run to do k small DFTs than one big DFT, and also in the sense, especially if you just compute it directly. Using the FFT, it's still a savings because the complexity is, I guess, super linear. It's beyond linear. The complexity grows faster than linear. And that's not to mention the fact that you could also parallelize this really easily, because if you're doing k DFTs, you can farm them out to different processors, whereas if you're doing one DFT, I don't know if it's parallelizable, actually, if the FFT is a parallelizable algorithm. I guess if you're doing a divide and conquer, it actually might be, because you'd effectively just be splitting everything into pieces, and then you could split and then farm out the pieces. So yeah, you actually could probably parallelize that algorithm. I'm not sure about other DFT methods, but anyway, that's a tangent. But it's still worth noting that it's not only is it has a lower variant, but this way of approaching it will also compute faster for very large time series data. So 2 big wins for Bartlett. And there's also another also. Also, there is Welch's method. And this is the same idea as Bartlett, but the, I guess, time series pieces can overlap. So what I mean by that is that if we go back up here, and I said we had our k disjoint pieces, in Welch's method they don't have to be disjoint. So it kind of generalizes the idea of Bartlett's method by allowing them to overlap a little bit. Ultimately, it gives you something very similar. I don't know, maybe some people prefer one over the other, or maybe they prefer Welch's method because of the generalizability to be able to overlap and get more windows. But I honestly don't have a strong sense of which one would be better than the other. They're both very similar in the way that they are written. All right, so that's just a way to average. And in this case, I want to point out we're averaging in a sense in the time domain in the sense that we're taking our time series data time-wise and we're breaking it into pieces, and then we're using those pieces to estimate the periodogram individually and then aggregating them all together in the end. The next topic that we need to talk about today is called banding. And banding is, in a sense, averaging, but in the spectral or in the frequency domain. So in this case, we partition the frequencies omega into bands. All right, so what's a band? Well, we'll say of length 2m plus 1. There's a reason why. Again, we want it to be an odd number, so I'm going to write it as 2m plus 1. Anyway, our frequency band, which we'll write as script B, is going to be, well, all of the frequencies such that for some omega j, well, let me write this all out first, less than or equal to omega less than or equal to omega j plus m over t. So what we're saying is that we want all of the frequencies omega that lie within some band around omega j. So if I take whatever omega j is, right, it's j divided by t or something, then what I'm going to do is I'm going to go out to the left or to the right, say m units, 1, 2, 3, 4. Let's say m is equal to 4, and the other way, 1, 2, 3, 4. And then I have my band of frequencies. In this case, we could have, like I said, I'll just put it in here, m equal to 4 in this example. So remember, all the frequencies we're looking at are going to end up being discrete in the sense that we can't estimate the periodogram for any given frequency, but just the ones corresponding to the, I guess, the sample size, capital T. Of course, we can always interpolate and things like that, but in this case, right, this is what we have. All right, so what do we have? Well, we have some terminology. We say that 2m plus 1 divided by t is the bandwidth, which is, yeah, a term that gets thrown around a lot. In this case, literally, it is the width of the band. In this case, right, we're thinking of the frequencies of running all the way from 0 to 1, omega going from 0 to 1. So in this case, by dividing by t, it's the fraction of the unit interval that's captured by this little red box here that I, bracket that I put in. All right, so what are we going to do with the bandwidth? So the idea, I didn't actually tell you what it is yet. I just said we can block off some frequencies. So given a band script B, we can average over all, not frequencies, I guess. We can average, we'll say, the spectral density over all frequencies in B. And the idea being that if fx omega is close to constant, for omega in B, then this improves the estimate. All right, so again, the idea is that it doesn't have to be exactly constant, but roughly what we're doing is, again, we're saying, okay, we have this big window of frequencies that we can estimate. Rather than estimating the spectral density at every given frequency, we'll take a chunk of frequencies, a band of frequencies, and we'll kind of average the spectral density over that band and just get one number out, which is sort of the average intensity or power or spectral density in that band of frequencies. Again, the idea being that, well, if there's a lot of noise in one of these, then if we average over, or in each of these, I should say, then if we average over many of them, we again get the same ideas above. We reduce the variance. That typically makes us happy when we get a lower variance. So, what does that look like mathematically? Well, mathematically, what we get is we get a periodogram, which also going to be terrible notation. We're going to call it I bar. And that is going to be for some omega. And what we're going to do is we're going to average over all of the 2m plus 1 frequencies within the band that we have constructed, which is going to look something like this. So in this case, yeah, there we are. So in this case, what we do is, right, we compute the, this is the standard. Maybe I shouldn't say standard periodogram, because that's going to make it sound like it's, I just mean the periodogram from before. And over here, we have the average. The averaged periodogram. So what it means is that we're just taking, again, all of the frequencies that lie within that band B, and we're giving them the same value, which is the average of, well, all the periodogram values inside that band. So what happens mathematically when we do this? Well, first what we'll say is recall from last time that if I take I omega j and to the t, because I have to have we're going to do that limit again, and I have to have a sequence of omega j's that changes with t. So if we take this thing and we multiply by 2 and we divide by the spectral density at the given, I guess, frequency of interest, then this thing converges in distribution to a chi-squared random variable with 2 degrees of freedom. Right, so we did that, I think, at the very end of the lecture from last time. Well, what happens with I bar? Well, we'll say for I bar, and again, there are some conditions like that strong, I think, summability condition for the autocovariance, if I recall from last time. You can double check those yourself, but in this case, what I'll say is for I bar omega, we get something very similar. What we get is that 2 times the length of this whole thing, 2m plus 1, times the estimate, I bar omega j to the capital T. Remember, that's a sequence of omega j's in t as t goes to infinity. I guess I should also put that up here. As t goes to infinity. And I guess, omega j converges to something. Yes, then we have to divide by the spectral. I should put an x in here for the two spectral densities again. All right, so this thing, well, what's it going to converge to? Like, what does it make? What do you think the answer is? Well, if one of these guys goes to a chi-squared with 2 degrees of freedom, and now we have 2m plus one of these guys, it's going to converge to a chi-squared distribution with 2 times 2m plus 1, which is 4m plus 2 degrees of freedom. All right. So what we have here, right, is another type of convergence, again, given that the conditions are satisfied. And we're getting a chi-square distribution with more degrees of freedom, so that's nice, I guess. And similarly, from here, what we could do is we could go back to what we did in the previous lecture, and we could actually construct confidence bands. So I guess just for completeness, I'll write it out. We can then get, I should say, confidence intervals, I guess, because these are pointwise. Confidence intervals that look like, well, if I just multiply the 2 in there, I'm going to get a 4m plus 2i bar. I hate that notation. I got to think of a better one, but no time to think of a better notation right now. Well, if we divide this by our chi-squared with 4m plus 2 degrees of freedom, 1 minus alpha, over 2, we have the spectral density in there, and then the same thing on the upper, the right-hand side, that is. Except that, yeah, with the new chi-square distribution for the denominator, alpha over 2. Cool, so we have a confidence band, and we get a, well, we get a different chi-square distribution, and we get a different coefficient out front now in terms of how big m is. All right, so what do we go from there? All right, so it's worth noting that this works. There's one other thing that's a note, is that this works for large t, right? Because it's an asymptotic result as t goes to infinity. So if t is large enough to be asymptotic, then okay, we can believe this works. But also for large t and for small m, we can't have m be too big or it's going to kind of mess up the asymptotics of this whole thing. So typically you might have m be a small number that's just going to kind of average some of the local frequencies together. So again, it has a very similar thought process to what we did with Bartlett's method. It's just slightly different in the way we approach it, right? Bartlett's method took the data, broke it up into disjoint pieces, and then averaged all of the estimates together. In this case, what we're doing is we're taking local frequencies and averaging them all together. It's kind of neat, though, because it has a similar idea, which is in Bartlett's method, we have fewer frequencies that we're able to estimate the periodogram at. And similarly here, we're just taking a bunch of frequencies and averaging them together. So again, we have fewer frequencies in total that we have for our periodogram. So there's a lot of similarities in these ideas, even though one is more, I guess, time domain and one is more frequency domain in its approach. All right, so going forward with banding still,
we could also try non-uniform weights. What that means is that in the equation up above, what we had was that I was averaging all of these periodograms together, and I gave them all the same weight, which is 1 over 2m plus 1. But what I could do, right, is I could add weights in there, and I could give them different weights for averaging. So what would that look like? Yes. So what that would look like, and I'm going to call this I tilde just to indicate that it is a weighted estimate or averaging of the periodograms. And in this case, what we get is something that's going to look like I from minus m to plus m. I'm still going to use the total width, I guess, as being 2m plus 1. But in this case, we're going to multiply by ci times our periodogram, omega j plus I over t. Now, in this case, we also need where the coefficients ci sum up to 1. Right? So if ci is just equal to 1 over 2m plus 1, then we're just back where we were up here. But the point being that is we could choose ci's that are not just all the same value, and that can give us a different way to average the or to get a weighted average of the periodograms for banding. Right, so what happens mathematically? Okay, so in this case, we still get convergence in distribution as before. Okay, so we're going to get a convergent distribution given all the nice conditions that we talked about previously, like the, I guess, convergence of the, I guess, spectral, not spectral density, autocovariance and things like that. But there is one issue. We're not going to get a chi-square distribution. We're going to get a weighted sum of chi-square distributions, which is actually kind of annoying to work with when you want to compute critical values, thresholds, p-values, things like that. It's actually, I think there are a bunch of crazy methods out there, and you can find them somewhere in R. I remember finding a package with like 5 or 6 different methods for numerically computing various thresholds and critical points for a weighted sum of chi-squareds. So we can do that, but instead we can also just kind of hand wave our way past it. Anyway, we do require, I'll write that down in a second, but what we require to get this convergence is a couple things. We require, of course, t going to infinity, and we can take m to infinity as well, but such that m divided by t goes to 0. So what does that mean? Well, that means that the width of our band, I guess, our bandwidth, can, but not exactly the bandwidth. It's the m value is allowed to grow, but it has to grow slower than t grows. So as we go to infinity, the actual bandwidth, which is the length of the band divided by t, will actually go to 0. So it'll actually shrink to 0, and that's why it can be a little confusing to look to. I feel like the term bandwidth is a bit confusing here. Anyway, we need this, and we need another condition, which is that I from minus m to m of the ci squared, these coefficients, we need this thing to go to 0. So this can work basically as long as the coefficients, I guess, kind of don't peak at some value. Like they don't all just go to 1, or not all, but if like the main coefficient doesn't tend towards 1 or anything, then as long as we have them squared, and they should sort of vanish in some sense. Anyway, given all of this, what do we get? Well, what we get is that the expected value of this I tilde omega j thing, our weighted average, or weighted averaging of the periodogram, is going to converge. The expected value, I should say, is going to converge to omega, to the spectral density at omega. I guess I should say, well, I'll just get rid of the j there. We'll just say omega omega. Okay, what does that mean? Well, remember, this is not convergence in probability. We've already taken an expectation. So the thing that's converging is not a random variable anymore. What this means is that we have an asymptotically unbiased. And that's nice, because if we want to do things like confidence intervals or whatnot, at least asymptotically, we'd like things to be unbiased. Right, so it basically means, I'm guessing, I didn't actually find a good formula for the expected value of this thing. I guess we could work it out if we really wanted to try, but I guess there'd be some covariance in there, so it would be a pain. Never mind, we're not going to worry about that. The point is that there might be some bias here, but it asymptotically vanishes, and we get something that estimates the spectral density just like we want. Furthermore, if we look at the covariance of our I tilde omega 1 and I tilde omega 2, so if we have two different frequencies and we compute their covariance and we normalize this whole crazy thing by the sum of minus m to plus m of ci squared, then in the limit, this thing is going to converge to, well, 0 for omega 1 not equal to omega 2, which is good. That means that at two distinct frequencies, we get that in the limit, our estimator is uncorrelated. We get that the variance converges to the spectral density squared, again for omega 1 equal to omega 2, which is neither 0 and also not equal to 1/2. If it is in one of those cases, we end up multiplying the whole thing by 2. Omega 1 equal to omega 2 equal to 0 or equal to 1/2. Those are like the fringe, the edge cases. All right, so as I mentioned above here, in the limit, we get a weighted sum of chi-squared random variables, which is never really that great to work with. So instead, but this is close, which I'm going to put in quotes because I'm not actually sure how close it is and in what metric it's considered close. This is more of just a hand-wavy statement to a, let's say, not weighted, regular chi-squared random variable with, we're going to say, 2L degrees of freedom. where what is L? Where L is the length of this band. Okay, so how do we define the length? Well, what we define the length to be is that L is going to be, well, it's the sum of all those coefficients, I from minus m to m of ci squared to the minus 1. Okay, so you look at that and you think to yourself, well, why in the world is that supposed to be the length? Well, let's do an example. For example, if ci is just equal to 1 over 2m plus 1 for all I, then what we end up with, then we get a length, which is going to look like the sum of 1 over 2m plus 1 squared minus 1, which is going to be, well, 2m plus 1 over 2m plus 1 squared to the minus 1, which is just 2m plus 1. So the notion of length coincides with what happens when all the weights are equal to each other. If the weights are not equal to each other, then we get that this is, I guess, good enough, at least according to the textbook authors who said this. And I guess they're trustworthy enough, so why not believe them? Anyway, it'll be interesting when we look at this in R to see how this actually works in practice. There we go. Batteries are dying. There we go. We are back. Anyway, okay, so that's our little example. I'll block that off. Thus, we have that 2 times L, the length, times I tilde at some omega j with the t in there, divided by the spectral density at that omega j with the t in there, is going to converge in distribution to a chi-squared 2L. This is, there's no like approximate convergence. Close enough, I guess, to the weighted chi-squared distribution. The sum of a bunch of weighted, or I guess the weighted sum of a bunch of chi-squared distributions. Okay, so we got that, and once again, if I really wanted to, I could go back up here and compute a confidence band or interval for the spectral density using that new version of the length, that more generalized version of the length of our band, and also the corresponding degrees of freedom. But I'm not going to write that again because it should be pretty clear how that would just come about. Okay, so then the next thing is how in the world do we pick a good weighting scheme? So how to pick the, I think I was calling them C, right? CIs. CIs. Well, if you look at some of the functions in R, which we will look at probably in the next lecture, one of the things, or one of the terms that you'll see being thrown around in the documentation is that we could use the Daniel kernel, which then leads to the question of what's the Daniel kernel. Well, if you type that into Google, if you type it in with Daniel with 1L, you get random Facebook pages for people named Daniel Kernel, which is just awesome that that actually exists. And since this is going up on YouTube, If there's any chance that Daniel Kernel or any of the Daniel Kernels out there are watching this, then give a shout out in the comments, because I would love to know that. Though, based on the fact that I don't think too many people are really going to watch this, I'm not expecting anybody named Daniel Kernel to actually watch this. If you type in Daniel with 2 L's, Kernel, then you get a whole bunch of time series references. So remember, it's Daniel with 2 L's. Otherwise, you get some random people. Regardless, the idea is that this shows up a lot in R. If you look at a lot of the functions that we have for computing the spectral density, they'll say things like, this uses the Daniel kernel or something of that nature. So the question is then, what is the Daniel kernel? Well, so first, we'll say let ut be some sequence of numbers, mainly because I don't really want to have to do this with the I omegas, because the indices will get super annoying. So instead, we're just going to apply this kernel to a sequence ut. It doesn't even really have to be a time series. It just has to be a sequence of numbers. So one application gives us a new sequence of numbers ut1, which is going to be the average of ut at time t minus 1 plus ut at time, or u at time t, and u at t plus 1. And we're going to divide all of these by 3. Cool. All right, so the first thing you're thinking, well, that's kind of boring, right? Because that's just equally weighted. That's m is equal to 1, and it's just equally weighted. So why does that get a special name? Well, it's not so much that it gets a special name for using it once, but the fact that we can apply it a second time to get 2 applications of this kernel gives us a new weighting scheme, which is going to look like, well, the same thing as above. ut plus let's see if we can do this, plus 1, but I'm going to apply this to the already, I guess, kerneled series or sequence. So if I kind of revert this back into the original sequence ut with no exponents, what I end up with is actually something like a ut minus 2, ut minus 1, ut plus 1, ut plus 2. We divide all of these by 9, but now they're weighted. So this gets a plus and a 2, a plus and a 3, a plus and a 2, a plus and just a 1. So I'm not going to write anything there. So one application is going to give us weights that look like this: 1/3, 1/3, 1/3, where as I write 1/2, 1/3, 1/3, and 1/3. Meanwhile, 2 applications is going to give us something that looks like a triangle. With our 1/9, 2/9, 3/9, etc. And if we were to do it a third time, I'm not going to write it all out, we'd get something that might look a little bit parabolic. This is very closely related to the idea that if I take the uniform distribution and I convolve it with itself, that is, if I add 2 uniform random variables together, I end up with a triangle-shaped distribution. If I add another 3 uniforms together, I get something that looks piecewise quadratic. and then piecewise cubic, and so on as I keep adding uniform distributions together, or as I keep adding uniform random variables together, which means I'm convolving the uniform distribution with itself so many times. And the same idea happens here. We're basically doing a convolution, but a discrete type of convolution. So we go from something that looks constant to linear to quadratic and so on. So you can change the parameters in R to say, in some sense, how many times you want to apply this and how smooth you want your kernel to be. The kernel here is just referring to the weights. And there's also something called the modified Daniel kernel. The modified Daniel kernel. And that's just going to basically be do as before, but starting, I missed a word, but starting with UT1 being, well, UT minus 1, UT plus 1, but now we're going to divide by 4, even though my 4 looks a bit like a U. And we're going to give it a weight of, the middle guy, a weight of 2. So it's the same thing, but what now we're doing is we're giving the middle guy a little bit of a bigger weight, and the 2 edge pieces a little bit less of a weight. And you're already starting in kind of a triangular shape, I guess, before proceeding forward. So it's just a slightly different way of starting the whole thing. Probably doesn't make a huge difference in the end. We can try some examples out in R and see what happens. The main thing is just to be aware of the terminology, right? Because a lot of the packages like to throw all these things around, like Bartlett method. I think there's a Bartlett window, or we're going to talk about in a second. Bartlett this, and Daniel kernel that, and modified Daniel kernel, and all these parameters. And you just think to yourself, what in the world are they talking about? Well, it's nothing too profound. It's basically just throw some weights on your periodogram and average them together in a weighted fashion. All right, so that wraps up what I wanted to talk about with banding. So that means we have the next topic is tapering. All right, so the next thing we're going to talk about is the idea of tapering. And tapering is kind of what you might expect. It's basically applying some type of weight to your time series that kind of tapers off at the ends. And focuses on the middle. Now, yeah, it basically allows us to focus on certain frequencies for our spectral density. But we're going to look at this in the time domain, actually, to start. And like most cases, there's ways of going back and forth between time and frequency, and we're certainly going to be doing that here. In this case, we need to, once again, say let xt be mean 0 and stationary, as almost always, but just to emphasize, we need that. With spectral density, which is what? Well, it's what it always is, fx omega. But now what we're going to do is we're going to bring in a tapered y. So we'll say let yt be, what's my notation here, at times xt be the tapered series. Again, we'll see in a second that sometimes you'll apply some tapering that'll kind of focus on the middle of the data set and smooth that, and kind of less emphasis on the edges, or the further out pieces on either side of time. right? So if we have this, this is, I should say, for some AT in R. So some just real valued coefficients that we're not going to specify at the moment. So then the discrete Fourier transform is what? Well, dy at omega j is going to be 1 over, it still has the same data size, the square root of t, and we're going to be summing I from 1 to capital T, and we're taking our data, which in this case is going to be AT xt, and multiplying by that complex exponential to get our Fourier transform, or our discrete Fourier transform. All right, so what do we get from there? Well, then we find out that the expected value of the periodogram, right? Because we want to ultimately know what does the I mean, we're doing this transformation. What's going to happen to our periodogram? Well, if we look at the expected value of our periodogram, it's no longer just going to be the spectral density. We don't have some unbiased estimator. Instead, what we're doing is we are integrating from 1/2 minus 1/2 to plus 1/2 of WT omega j, W's and omegas, omega fx omega d omega. Okay, a lot of omegas. What does that mean? Well, what that means is that if we want to know what the expected value of the periodogram is for y, right, which would be an estimator of the spectral density for the tapered series y, what we find on the other side is we have an integral with respect to the spectral density in x, but we're multiplying by some w thing, and the w is going to be called the spectral window. A lot of terminology, but there's gonna be some intuition here, which should hopefully help us. But first, I have to write down all this stuff. We'll say where Wt of, we'll just say omega here, is going to be the squared modulus of At omega, where, to continue our iterative wheres, At is kind of like that thing we had before, right? It's going to be the discrete Fourier transform of our sequence At. Right, we had something very similar to this before when we talked about filtering a time series, and specifically an ARMA process. Okay, so again, capital A of omega is the Fourier transform of the little a sequence, and Wt is the squared modulus of the A, capital A, and that's going to be called the spectral window. All right, so then the question is, what what is going on here? Well, if we have an example, well, I guess I have an example. Well, let me not do that example yet. We'll say the spectral window may look something like, well, centered around 0 because we're offsetting it by omega j. It might look something like this. It's supposed to be symmetric. I can only draw so symmetric at this point in the term. So our WT omega might look something like this for the omega axis here. And what it means is that our periodogram for Y is taking a range of frequencies and averaging the spectral density for X over that range of frequencies. So it is very similar in a sense to what we already did before. Right before what we did, just to recall, because these things are all very similar, but they are also different. What we did before up here is that we said, I'm going to compute my periodogram at lots of different frequencies, and then I'm going to average together some local frequencies. Here, what we're doing is we're modifying the original data, the original data X, and the effect of modifying the original data is to ultimately average the spectral density over some window WT, where WT, they have some pictures, and I'll get some in R next time when I can actually plot them all. But the pictures of these windows often look like that, where you have some sort of a peak part, and then it kind of tapers off pretty fast. So this is kind of neat. It means that if we apply a tapering to the time series itself, X, the effect that we're getting is an averaging, a window being integrated with respect to, it's actually a convolution, I guess, but with respect to our spectral density F here. But the end result is the same, right? If I'm integrating over all these frequencies, I'm effectively averaging the spectral density over some window of frequencies. So very similar intuition to banding, but it is a different thing altogether. Well, not altogether, but it's a different thing. Anyway, we do have an example, and this is more random terminology that you might run across when you're looking at time series methods. And this is the Fege or Bartlett, because of course he got his name on this one too, kernel. So, okay, we got two different names for this one, depending on, I guess, who wrote it, who writes the textbook or the documentation. And this is a kernel. It's a window function, the spectral window. Oftentimes when you integrate with respect to something like W, it's referred to as a kernel function. Kernel is one of those terms in math that is way overloaded, right? You've got kernels in linear algebra, kernel spaces. You've got integration kernels. You've got the kernel trick in machine learning. You've got reproducing kernel Hilbert spaces and all. I mean, a lot of these kernels are all integration kernels, but still, the term kernel is just all over the place in math. I'm going to make this W look more like a W and less like an omega. Okay, anyway, the Bartlett or Fege kernel is going to look something like the sine of n pi omega squared divided by n outside of this sine pi omega squared. Okay, so why is that the case? Oh, with WT at 0, because in that case I'd have 0 over 0, which is no good. That's going to just converge in the limit to n. If you were to take omega to 0 and you look at the limiting behavior of sine squared over sine squared, you'd end up with, well, n squared, which divided by this n here in the denominator would get you that at 0 it's equal to n. Except now that I think about it, I actually meant to say t, because some textbooks use n as the data size, whereas I like to use t as the total size of my time series. Okay, that looks better. All right, so what does this come from? This comes from AT equal to 1. Okay, so this comes from, in some sense, nothing. The idea is that if I go back up here and I set all the ATs equal to 1, and I just get, in that case, y is equal to x. And then what I end up with is, well, my capital A is going to just be the sum of these complex exponentials, and when I do the squared modulus of that, I get something out that looks like this. I haven't actually checked that myself. Maybe we can actually write it all out and check it, but yeah, not in this lecture, because we can see if that actually works out. Roughly, it's just a way to note that we can integrate with respect to this kernel. But more interestingly is not this kernel, but what happens when we do that averaging from above. So, banding, that is. When we average over a band, script B, as before, then, well, what happens? Then what happens is, I know it's here somewhere. Ah, yeah. What we end up with is let's just write it out, not the weighted one. The weighted one's just going to be harder to figure out. Then what we end up with is something that looks like I omega, which is just 1 over 2m plus 1. Same thing I wrote before, but just to make sure it's all on the same section or the same slide, I'll write it again. Right, what we do is we average over all these periodograms like that. Well, it turns out that this is equivalent to tapering with a specific spectral window, and that then I'll say this gives us a W T omega, which so happens to just be 1 over 2m plus 1 times the sum I from minus m to plus m of, well, that exact same kernel above. The sine of n pi omega plus I over t. So that same kernel, but offset by some phase in terms of the adjacent frequencies that we're averaging over. And then we have pi with no n, because the n is outside the sign now, I over t squared. Whew. Okay, so that's another big formula. But the thing is, it's basically saying that if we were to, when we apply this banding where we're averaging over all of the periodogram values for frequencies that lie within a given band, we can equivalently write that if we switch into this other setting as integrating the spectral density with respect to some spectral window, and the spectral window happens to look like that semi-hideous ratio of squared sines. So again, not the nicest looking thing, but it's nice to see how these things all connect together. And I'll draw some more pictures. But of note, we note that typically tapering in the sense of putting less weight on far, I'll say, how do I even describe this? I guess it's like time points that are not near the center. Less weight on time points far from t over 2 and more on those close to t over 2, the center of our time series, I guess, temporally, will often improve performance. And we'll look at some examples of this when we do some R code, but roughly, well, one of the standard, maybe I'll just write it down, one standard choice is the, and here's more terminology, the, what is it called, cosine? The cosine taper. Okay, simple enough. The cosine taper. This one is in the AT, or time domain. In this case, we take AT and we simply say that it is equal to 1 plus the cosine of, okay, let's see if I can get all these parentheses correct. It should be 2 pi t minus t plus 1 over 2 divided by t. Something like that. I think in this whole thing gets a 1/2 out front that I forgot to write. Okay, so that looks a little bit strange, but ultimately all we're saying is that I have something, no, not there, I need it here, the axis here, because if we start from 1 and 2, and then somewhere in the middle here we're at, I guess, in this case, t plus 1 over 2, and then t. So if we have our entire, maybe I should change these to t plus 1 up here just to coincide with that. So if we stare at this function long enough, we realize that what we have is we basically have a cosine function that reaches its peak in the center, because when little t is equal to capital T plus 1 over 2, this thing becomes 0. Cosine of 0 is 1, plus 1 is 2, divided by 2 is 1. So we're right up here at 1. As we move to the outer limits here, we're getting a cosine that is going to be very close to, well, pi, I guess, which is close to 0, which is going to take, or no, it's going to be close to -1. So, but at -1, we're going to add a +1, so it's still going to not be negative. So it should look something kind of like this, I guess. So, okay, it might seem a little strange, because why are we kind of down weighting our data? But effectively what we're doing here is we are putting less emphasis on the boundary points of our data, more emphasis on the middle points of our data set. We apply that first, then we use that to compute, say, the spectral density and whatnot. And what we get out is something that, well, allegedly is better. Now, I'm not going to, won't go into that now. I guess I should. I'm not going to go into that now. What we'll do in the next lecture is we'll actually look at some R code. There's one more thing I did want to talk about, but I think I'll just save it for the next lecture, and that's the idea of using the ARMA process or estimating an ARMA process in order to estimate a spectral density. It's one more technique, and I think what we'll do is we'll save that for next time, then we'll do some R code, because all of this stuff is possible in R, and it'll give us a lot of different examples to look at, so we can get a sense of, okay, what happens when we compute a periodogram. We did this before, but we did this very manually using the FFT function. In R, there are different spectrum functions that you can use to estimate the spectrum or the spectral density for a time series data, and using many different methods like the ones we discussed today. So how's that all work? Well, I guess tune in next time and we will take a look at all of this in R. And until then, well, have a good one, and see you in the next lecture.